All right. Higher order functions. So this is an example of a higher order function. Um, let's actually ask the class. Can somebody tell me what a higher order function is?
I can take a stab at it if you want.
Sure.
Uh, I think it's anytime a function is like takes another function and uses that as input in its own function, or when a function produces an output for another function. So I guess more broadly, whenever like functions are integrated together.
Exactly. Awesome. That's exactly it. Does anyone want to take a stab at why they're called higher order functions?
Does it have to do with it means that the language can support like functions as first class objects? I don't know if I'm way off here.
Yeah, actually, that's actually, I would say that's a pretty good way of summarizing it. Yes. So I guess the other way of talking it through that I was expecting was that, well, I mean, that essentially is the answer, right? So basically, when we're dealing with regular data types, right, like strings, numbers, Booleans, etc., these are your primitive and complex data types. What we're dealing with is basically, yeah, first class data types. And so when you're working with this, your function is just called a first order function. When your first order function starts to interact with other functions, then it becomes a higher order function. And the terminology really refers to the layer of abstraction and complexity with the manipulation of this data. So why are they called higher order functions? Because functions that take in standard data types are referred to as first order functions. And that signifies the level of abstraction used when manipulating the data. Let's go back to that screen cap real quick and let's talk through what's happening here. We can think of, well, at the start, what we're actually using are lambda functions. And lambda functions are essentially just, I don't know if you could call them shorthand functions, but they are essentially simple functions. They're also referred to as anonymous functions because they are functions that we define without a name. And they utilize these arrows. So they're also referred to as arrow functions from time to time. So how is this a higher order function? Well, we're creating a constant, we're calling it add, and the value that we're setting this to is a lambda function. Lambdas, the syntax for lambdas are essentially parameters on the left, expressions on the right. So what's happening here is we have a lambda expression defining x as a parameter, with the expression being another function, and that's y as the parameter with x plus y as the expression. So what happens here then is we have a function called add, which we could use as a basis for additional functions. And here we're creating a new function. We're calling it add 10. And we say add 10 equals this original higher order function add, but you're passing in 10. So 10 becomes your x. Now, when we call this new function, we're calling add 10, and now we're passing in 20, which becomes your y. And these two together create 30. So again, Lambda function syntax is pretty simple. These are useful for just quick and dirty code. It's good for when you want to write succinct code or when you have some kind of complex behavior that requires a lot of really simple data manipulation. We're also going to be seeing a lot of this in React. So definitely something that you will become more familiar with and comfortable with over time. Also very heavily used in TypeScript. Now, we're talking about a lot of different function types, and there's kind of like a lot of I guess overlap here, because in this case, not only do we have higher order functions, and not only are we using Lambda functions to write them out, but this is also an example of a curried function. And curried functions are essentially functions that take multiple arguments and it turns them into a sequence of functions. So again, it overlaps with higher order functions because higher order functions are in a way a sequence of functions. So with a curried function, however, each function is in the sequence, takes in a single argument. So we have one function that takes in X, one that takes in Y. And these allow you to partially apply the function, provide some of the arguments up front, and then obtain a new function that waits for the remaining arguments. So earlier we were creating a function called add10, which we then passed another argument to, the 20. We could also just pass both those arguments in right off the bat to this curried function. And so in the bottom part of the screen cap, we see add 10, 20 equals 30. Any questions so far? If it seems, I don't know, confusing because of the I don't know, kind of like Inception, there's a lot of like layering inside itself. It's really only the syntax, I think, that can be confusing about it. Eventually, once you start to play around with these yourself, you'll get a feel for the benefits of them. As you start to write code and become comfortable with writing code, and you start integrating these kind of shorthand or quicker expressions, you'll find that they do have value in creating cleaner, shorter, more concise code. And without them, we would have to utilize a lot of loops. There are built-in functions in JavaScript that out of the box are higher order functions. So when we use map, filter, reduce, these are all built-in JavaScript functions that allow us to iterate through some kind of iterable object and return an array without the ability to take in a function within another function. Without higher order functions, we would have to use for loops in order to achieve the same complexity. So that is higher order functions in a nutshell. The other thing that we're going to be covering today is recursion, which, like higher order functions, there's a sense of inception to it, right? So what is recursion? To understand recursion, one must first understand recursion. Not a real quote, I'm pretty sure, but the idea is that there's like an elegance to recursion, right? It's how's that saying go? What's that expression? Something brevity is the soul of wit. I'm terrible with memorizing these kind of expressions, but it's kind of like, think about fractals, or like how fractals reoccur in nature, right? Like there's a beauty or an elegance to how recursion is by design. And so it may not be, let's say, a concept that you apply on a very regular basis, but there are definitely use cases out there where recursion might be the solution you want. And so one of the reasons that we're studying these various ways to write functions or essentially accomplish the same things in the end is because you want to expand your toolkit, the number of ways you can achieve things. And recursion itself is good for reducing complexity, just like higher order functions. So brevity is levity. In a way, these additional layers of abstraction and complexity will challenge your mind in ways that writing these basic simple for loops will not, right? So it's kind of like creative outside of the box thinking that it's pushing you towards. And let's see, it's ultimately just another approach to solving algorithmic problems. And, all approaches are going to have their pros and cons. It's all going to be very contextual. What you use depends on your context, your goals, your use case. So your mileage might vary when it comes to these various approaches. But you won't necessarily know when it comes in handy until it comes in handy. So it's best to get a grasp for these as early as possible, and through experience, build them into your toolkit. Yes. Are these slides available in the slides link? I need to update that slides link. I think there is a shared drive folder that I should have used instead of the one I'm actually using, and you all should have access to that. So I will do that first thing after lecture. I'll move over the slides to the right folder or create a shortcut or symlink or something. 3 laws of recursion. A recursive algorithm must call itself. Recursive algorithms must have a base case, so essentially your simplest solution. And a recursive algorithm must change its state towards the base case, so reduction of complexity. When you're planning out a recursive function, this is how I like to think about it. You can think about it in steps. There's a process that you follow to make this a little easier to remember, but you generally want to start by identifying your base case, because that's going to be your starting point. As the simplest iteration of a recursive solution, it should be the easiest to identify and work through as an example. And from there, you can gather additional data, additional cases that your recursive solution can tackle. And as you create these additional cases, you can compare between the two. And by comparing, you could draw conclusions that will help you identify the pattern. And the pattern is what you're going to essentially create the code out of. I know this is very abstract right now, but bear with me. So let's think about factorials to start. We know that factorials are essentially when you take a number and you multiply it by the number preceding it and the number preceding that, and so on and so forth until you reach 1. The product of an integer and all non-negative integers below it, so n minus 1 to 0. This is an imperative or iterative way of writing solution, right, in this expression up here. So when we're doing n factorial, what we're doing is we're saying n times n minus 1 times n minus 2, so on and so forth, until we're just multiplying by 1. Recursively, you have shorter and more, I don't know, concise syntax. So n times n minus 1 factorial. The recursion happens in this n part of the expression, where it's essentially recalling itself to continue executing until it reaches 1. So imperative iterative solutions are essentially step-by-steps. They require less abstraction. They utilize loops and conditionals. And we use variables to help us build the solution as we go, right? So when we're like creating a for loop, we're defining I as an index, which allows us to iterate through the array or iterable object that we're dealing with. When we're working with something recursive, or when we're taking a recursive approach, I should say, to a function or an algorithm or a component, we are aiming for a self-referencing solution. So usually in the case of code, you're talking about a function that's going to call itself. And in this case, we have a function we're defining as factorial. It takes one argument, n. We see if n equals 1. If it does, then we return 1. Otherwise, we return n times the function itself. We're calling the function again. So recursion utilizes higher order functionality, like we learned earlier. When you calculate this, this is essentially multiplying n by the value before n, before the value, by the value before that, and so on and so forth, until we get the output of n factorial. Any questions? All right, cool. Let's take a look at today's module. We have higher order functions, and this will go a little more in depth into some of those methods I mentioned earlier, right? Like for each, map, filter, reduce. You can read through this to get an understanding on those methods. The recursion lesson, let's see. There's a good link to some additional reading. And a more in-depth explanation of recursion, and then some challenges. So today's challenges are going to be 3 for higher order functions and 2 for recursion. If you can't get through all of them, again, this is something that we can revisit throughout the curriculum just to keep us on our toes and ready for whiteboarding challenges and solving algorithm problems.
Julius, I think that recursive loop and recursion link is bringing me to a 404.
All right, let's take a look. Okay, I see. They're pointing to the previous repository. Let me update that.
In your job, is it possible to speak to any examples that you've used of these things? Or is that just kind of a crazy question because this is like basic stuff that I'm not getting?
I would say I definitely use higher order functionality a lot on front end work. But that's just, I think, the nature of React. I can't really think of any examples where I'm using a recursion, but there might be.
It's not exactly an example, but like I know isn't Haskell like in other languages, like they don't even have a way to loop. So like you literally can't program them if you can't do recursion pretty much.
Yeah, that's a good example. And Haskell it's a beast.
Yeah, I haven't had the motivation to check out that one yet.
Yeah, we had an instructor before that was very into Haskell. It was he tried to explain it to us once, and I could not keep up. I could not follow. I had no idea what was going on. Fun stuff.